Right, so let's quickly take a look at an example from the UCI machine learning repository. Then we'll do a recap of the Bayesian classification principles we talked about last time and the different kind of classifiers there. And the reason I want to talk about those is that it's really important to understand the fundamentals, right? It's important to understand what this is all about, right? And they're a good way of understanding that. And if we don't understand the simple things, we won't surely understand the complicated things. So we'll do a recap of that. Then I just want to show you that if you were to do your own implementations, what they might look like. So let's say you're doing something in a project at some point and you're thinking, oh, it could be nice to have these classifiers there. And I just want to show you how simple it might actually be. Because I know you're looking at the math, you think, oh, that looks complicated. You have a multivariate probability density function. How do I, what kind of computations do I actually need to compute, perform? And I'll just show you so you can see it's actually fairly simple. So then we'll talk about something called rejection class. And then we'll talk a lot about the two-class classification problem, which is also what we call detection. And in connection to that, we'll talk about the type of errors. Good. So what was this all about? Well, it was about us observing things in the real world. So what we might call objects, physical processes, or events, or whatever we may call it. We have a sensory system here that produces some measurements. Based on those, we perform pattern classification, where we assign a class to each of these object processes or events. Right? The measurements come in, label comes out. So here's an example of the, that's the one we actually looked at already. There is the example, so let's not spend any more time on that. Good. So the principle of Bayesian classification you can actually think of as being sort of a model of what's going on. In fact, you may think of it what you might call a generative model. So a model that spits out data that we then perform analysis of. So we have a bunch of classes, omega 1 through omega k here. So each of these is a class. We have k of them. We stuff these in a set here that we call omega here. And then each of these has a probability of occurring. They might be equal or they might be different. And it's you can think of it like if they were different flowers, it would be the probability of observing the different flowers without making any observations, right? So for example, if you flip a coin, before you flip the coin, you have an idea about the probabilities involved, right? There's two sides. And if the coin is produced properly, they will be equally likely, right? So in that case, they would have the same part, namely a half. We can imagine other kinds of things where they would not, the probability would not be the same. For example, different illnesses don't occur with the same frequency, right? Some illnesses are very common. These days, everybody is suffering from the flu or cold or stuff like that. And other diseases are really, really rare, fortunately. Okay, so imagine that we conduct an experiment where we draw these classes according to these priors. So like flipping a coin or something like that, just a bit more complicated, to decide which class we will spit out at this particular time. So we pick one class from the class here with these different probabilities here. This generates an object that we then perceive with the sensory system. The sensory system produces a measurement vector, also what we call feature vector, and then we perform pattern classification and we assign a class based on it. So we have these priors here, and there's a simple rule here which says that these priors must add up to 1, right? Such that all we might observe is explained by these different classes. And we can express the probability density function, the PDF of set here, as this sum here, all these conditional probability density functions here. And this one here is particularly important. This one is the prior, but this one here is the one that says how is the data distributed for the different classes. So if we go out in the world and measure collect a lot of feature vectors for different classes, we can build a model of this distribution. That's the basic idea. So we can go out, we can measure different kinds of, we can take pictures of different kinds of fruits and compute features from those, and we can try to build a statistical model of what that distribution here is for each class. What do the features look like for a tomato? What does it look like for an apple? What does it look like for an orange? And 9 years ago, when I was giving this course the first time, a student came to me and said, "Mess, I like your lectures, but I want to point out that a tomato is not a fruit." So I looked it up. A tomato is both a fruit and a vegetable, actually. Yeah. So you learn a lot of important stuff in this course. Okay? Good. And we can think of a classifier as a mathematical function that maps from a measurement, real measurement in dimensional space to the classes. If you want to be formal about it. If you were to put it in a block diagram, what's going on is that we're feeding, so now we're getting a new feature vector. For an object, we don't know what it is, and we want to find out what it is. So we take that feature vector here and we feed it to all the models we have of the different classes. So we compute the these are called likelihoods, by the way. We compute all these likelihoods for different classes here. We take that number, multiply it by the prior, and we do that for all the classes, and then we simply choose the one that's the largest. So if we take and assume that the data for each class, so the data for each class, not the data across classes, but the data for each class is normally distributed, but it's a multivariate normal distribution, then this probability density function here looks like this here. It says that the distribution of Z here is determined by two things: the covariance matrix CK for the class and the mean of the class. And my pen should be calibrated now, so now I can draw. No, what's going on, stupid pen? Damn it. Okay. Okay, this seems like an accident waiting to happen. I can just see the headlines. Professor killed in unfortunate accident involving whiteboard. So let's say we have a two-dimensional feature space here. So feature 1 and feature 2. Then what we're interested in is having a model of the data for each class. So it means, for example, if we have a mean here of one class there, the mean of another class here, and the mean of another class here, then we have part of the model here, because now we know something, but we don't know everything, right? We know the mean, the mu vector up there. That we know. The covariance matrix says how the data is distributed for each of the classes. And that we can illustrate with contours. And when you talk normal distributions, you know that you have a nice bell shape, right? And you go to multi-dimension, it's this nice bump you get, nice and smooth bump. And if you move along the contours there, what you're always going to get is something like a circle or an ellipse. So for example, here it might look like this. Here it might look like this, more around. Maybe this one's like this. So when you see these contours, this says something about what the covariance matrix of the distribution, what that looks like. Okay? In this case here, they have different shapes. And thus they must be different for the different classes. And this is why it's CK that's up there. Yeah. So if we can measure the covariance matrix and the mean here, we basically have a model like this of the data. We have a normal distribution for each of the classes, and we have this sort of combined model for the whole space. Where these means are in relation to each other and how the data is distributed determines whether this is an easy problem or a hard problem. If the means are very close, it's going to be hard. If the data is distributed such that they overlap a lot with these contours, it's going to be a hard problem. Okay? So, if you take this expression here and say you want to maximize it, you can rewrite it into this expression down here by simply taking the logarithm, such that logarithm cancels out with the exponential function here, and then otherwise you use these definitions here. Let's say we generate some data here in MATLAB. So here I have two covariance matrices. I have one here that you see here is 0 on the off diagonals here, and one that isn't. By the way, the elements we have here on the diagonal of a covariance matrix, what is that?
Variances.
These are variances, yeah. The off diagonals are covariances. What is covariance a measure of? They're a measure of statistical dependencies for Gaussian distributions. Oh, excuse me, normal distributions. In my world, in signal processing, we call it Gaussian distribution. And then other places they call it normal distribution. And then when I'm lecturing here, I get confused, and sometimes say normal, sometimes say Gaussian. I mean, it's the same. So don't be confused if I say Gaussian distribution. So here, for example, you have zeros here. This means that the two variables, so this two-dimensional example, this means that the two variables are statistically independent, because if things are normally distributed and uncorrelated, they're statistically independent. On the other hand, this one over here indicates there's a negative correlation between the two variables. What does that mean? It means that if one goes up, the other tends to go down, right? You can actually see this when you plot these contours, because if things are independent, so if we have this case here where the covariance matrix is diagonal like this here, it means that the covariance, the distribution's contours must either be circled or they can be stretched along one of the dimensions. So we can have a mean here, and then it can be stretched in this direction here, because this what the difference between this and this is that the variance is not the same among the different variables, for the different variables. So up here, for example, it's 1 for the first one and 2 for the second one. So that would be something like this here. If, however, the data looks like this, it means there's correlation between the variables, the features. In this case, it will be positive correlation, because if this variable gets larger, the other one also tends to get larger. If it's like this, it's negative correlation. So when you look at a scatter plot of some data, you can kind of get an idea about what kind of what this is going to look like. Okay? Or conversely, if you compute the covariance matrix, you can look at it and say, huh, looks like the two variables actually correlate. Then you know what it's going to look like. So in this case, I'm generating this artificially, of course. I'm not measuring anything. But I'm giving the two different covariance matrices, and I'm assigning a mean value 1.3 and minus 1, 1,3 and minus 1, 0 here as the two passes. So that would be 1.3 here, and the other one was minus 1. 0, so it would be here. So one mean is there and the other is there. And this one here was stretched along the second dimension, so the covariance is something like this. And this one was negatively correlated, so something like this. Yeah. Now, let's take these expressions and put them into these equations here and do these computations and see what we get. So 1 divided by square root 2 pi to the power 2 times the determinant of covariance matrix for the first class, and then exponential function. I can see that I forgot to divide by 2 up here. At least I was consistent in making an error, so it doesn't make a difference. Yeah. So, and I subtract the measurement vector from the mean from the measurement vector here, multiplied by the inverse covariance matrix here, and then multiplied by z minus the mean vector again, and multiplied by the prior. Then I get this number here. I do the same for the second class, and I get this number here. And the measurement vector I'm using is this one here. So it's 0.5, that's here, and then 0.5, so that's here. Which class do you think it belongs to? Number 1 and number 2? 2, right? And this is also what the math says, right? So our intuition here from drawing it checks out with the math when we actually do the computations. Yeah?
That number again, is that like the distance from the
you can think of it at distance, but then it's more convenient to use the logarithm expression that I had before. There were these other simple cases. Do we have them on? Yes, I have the special cases on the next slide here, so we can take a look at that. So, but it is a kind of distance, you might say. Yeah. Anyway, so you can see that these visual geometric interpretations here, they check out with the math. So I just want to show you how you can do these computations. Good. So if we say that, again, we can think of this as every measurement we have is generated by some model we impose on the problem. And of course that model might be good or it might be bad. But for example, we might say, we think what really separates these classes are the mean values, and the mean values alone, but that the covariance matrices are actually the same across classes. That would mean we have something, maybe we have a mean value here and we have a mean value here, and then both are distributed like this. Okay. And this might be the case, for example, if you're using, if the variation in the data you're seeing is due to noise in the equipment you're using, and you're using the same equipment all the time. By the way, when you're looking at this kind of model, you might wonder, is this really how the world is? No, it's a model of the world. So let's say for example that you're not equally tall, right? With this kind of model here, we're saying actually you're all equally tall, but the reason we're seeing a variation here is because of measurement errors. Okay? Or you could say we're not equally tall, but we all have how tall we are can be seen as a mean value and then a normal distribution around that, right? But it's actually the same model, right? But it's funny to think about it like that. So again, you can think of this as a generative model of how tall you are, your height. So if we were to generate your height randomly, we pick a mean value and we pick a covariance, or in this case a variance, and then we can generate data that looks just like the data of how tall you are. So that's one way of thinking about it. Same here. Maybe the covariance matrix is truly the same, for each class because of the way data is distributed within the class. Or all the data actually has the same value, but then the rest is just noise. Right? Two different ways of looking at the same model. Yeah, but anyways, so if we say the covariance matrix is the same, we end up with a simpler expression for the classifier, the base classifier. It ends up looking like this here. And this does not have, you see here there's a quadratic term here. So this actually goes away when we assume that the covariance matrix is the same. And so this yields this, what you call a linear classifier. As we talked about last time, the classifier from before here is what you call a quadratic classifier, and it has these quadratic curved decision boundaries in between classes. The linear one has hyperplanes in between the classes. So you see that the quadratic one is more sophisticated. In this case, you understand that the sophistication comes from assuming that the normal distribution has covariances that are different for the different classes. Yeah. So, oh yeah. And this one here, if you, going back to your question there about distances, this you can interpret as a distance. Actually, this is something called this is a weighted way of measuring Euclidean distances from the data point to the mean values. And this is what you call Mahalanobis distances. But if you then assume that the distribution is white, and white is an engineering term here. It's like you've heard of white noise, right? And white noise is something that has all equal frequencies, and all equal frequencies means that it has a flat spectrum. Something that has a flat spectrum has a diagonal covariance matrix. Yeah. It's a bit of a convoluted way of explaining it, but this is where the terminology comes from. What it means is that the covariance matrix is a scale identity matrix. This is this case up here. So if all your classes, if you look at a scatter plot, have something that looks like circular contours, this might be a good model of the data. If you take that and plug it into the classifier from before, you get this expression down here. This here is just a constant, it's not a constant across classes, but this involves the prior here. And what you have here is exactly the distance between your measurement vector and the mean. So this is exactly measuring distances. In PO tools, you can do it with NMSC. If you have equal priors, you can use NMC. If you have equal priors, then this term disappears, and it's just measuring how far is your measurement vector from the mean of the different classes. And then it's simply assigned to the class that is the class. So it's that simple. Yeah. LDC is implemented in PO tools with a function called LDC, and the quadratic classifier is something called QDC. So there you already have a bunch of classifiers you can try out. Yeah.
So I guess it would be necessary to check for normal distribution before picking a classifier, right? But,
yeah.
But at the same time, we can pick different classifiers and see how well they do without checking normal distribution, right?
But once we've done that, we can think about what the differences is between the classifiers. Because sometimes you'll end up in a situation where the LDC will be better than QDC, even though QDC was supposed to be better, right? If you have curved decision boundaries, that can reduce to a hyperplane, right? So how come a hyperplane can sometimes be better? How can something simpler be better? And there are good explanations for that. And this is why there is no clear answer to, which method is going to be best. If we just had one method that was always the best, we don't need to teach that method, right? Well, now everybody thinks it's the deep learning methods, right? But 10 years ago, they thought it was support vector machines. And 10 years before that, they thought it was something else. So probably something else is going to come along. And this is why we need to understand what we're doing here, so we can take the knowledge we have, we can generalize, and we can adapt to what's going on there. Yeah. So, but analyzing and checking for normality in a multidimensional space is actually quite difficult. You can of course do simple things like look at scatter plots, but how do you look at scatter plots for something that has 100 dimensions? It's not so easy, huh? But you should try to look at your data, looking at combinations of features, for example. Because if those are not normally distributed, then the whole thing is not normally distributed, right? But you can actually have that the individual parts are normally distributed, but the combination is not. So here's an example of a MATLAB implementation of this, and this is what you call the training. The training is when you gather data, assign labels to it, and then you measure, in this case, the mean values in the covariance matrices for each class. That's what we call training. So here I load something called training sets. I get the number of classes and the number of vectors I have in here. Then I loop over all classes here. I compute the mean for so I have a k here, that's the index for the classes, right? So here I compute the mean with the mean function. I use get data on the select data output on the data set, comma k. Cell that x, comma k selects the data belonging to class k from your data set x. And get data takes this structure and only retrieves the parts that's what we call the measurement of feature vectors. Similarly, we can compute the covariance matrix with the cov function here. And we can compute how much data we have for the different classes and divide by the total number of vectors we have. That's the prior, right? So if 40 vectors out of 100 belong to a certain class, then the prior for that class is 40%. Okay? Assuming that the data was collected such that it represents the natural probability of sampling the different classes, which might not be the case, right? In fact, often if you look at machine learning problems, people try to collect equal amounts of data for different classes. And that doesn't mean that they will occur equal likely out there in nature. So the last 3 lines here is the computation of that's the computation of these 3 quantities here. The one I call scalar, vector, matrix. Here's the matrix, the inverse covariance matrix. Here's the vector, 2 times the inverse class covariance matrix times the mean. And here's the scalar, the minus log determinant, blah, 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 blah. Right? So it's actually not something that requires a million lines of code to implement. So the next step is what we call test. So in the test here, we load the data, we measure the number of vectors we have. Now we take and run get data on Y, so we throw away the labels. So in X, we don't have access to the labels, right? And when you're testing things, you want to ignore the labels, right? You want to try to see if you can figure out what the labels are supposed to be. So here's a loop over the different vectors here. So we retrieve the feature vector here for the M feature vector here, and we compute the expression we had on the previous slide. And this produces J here, and then we choose the maximum J. And then the index there is the label we assigned to the object X. Okay. Then to compute the error rates here, we compare these C's here to the labels we have in Y, and divide by the total number of vectors. Yeah. This is what we call a test, right? The first phase, we trained it, we measured the quantities we needed to classify. The second phase, we were trying to figure out how well does it work. And actually, in this example here, I'm doing something that you should never ever do when you test classifiers. I'm actually running it on the same data that I'm training it on. You don't do that. Then the machine learning police will come after you. The thing is, of course, that if you train on the same data that you test on, right? If you optimize something for a particular data set, this is essentially what this is, optimization. Then, of course, it should work well on that data, right? So if you really want to know how well something is going to work when you put it out there in the real world, you should take some different data. We'll talk more about that later on in the course. And I think now also with all the deep learning stuff we're also seeing that the way the books have taught us how to do this are actually not good enough. We have to do something more radical. Sagi here experienced this last semester, right, Sagi? Sagi was very inspired by all these advances made in these deep learning methods. And he was working on classifying different acoustical environments. So recognizing what kind of environment you're in. What were the classes? It was
like beach,
restaurant, yeah,
train.
train, and stuff like that, yeah. And then Saki worked the entire semester on training deep neural networks to figure that stuff out. And then he had something that worked better than the state of the art. That was fantastic. So what was it? What is the classification rate?
98.
98%. That's pretty good, huh? And then Saki and I would discuss that, maybe you should try it on some different data. And then the performance dropped to, what was it? 53%, right? So we thought it worked. Its performance was 98%, but then it was 53. That's not so good, huh? The testing here, of course, part of the reason you test is to figure out if you're doing something wrong. But another reason you test is because you want to give people an idea of how well this is going to work. Is it a solved problem? So something working 98% of the time, that's probably very close to being a solved problem, right? The speech recognizer in my car does not work 98% of the time. In fact, I would say it hardly ever works. Yeah. So, what we really want to know is that how does it generalize? Can we train on this data here and then apply it on something else? Do the models we have trained, do they generalize to other data? And if so, at what cost? What is the degradation at cost we see? Yeah, so let me talk about the rejection class and then we can take a break. So the rejection class is an extra class that we can sort of artificially introduce. What's special about it is that we don't train a model for it. If you think back to the nuts and bolts example, we had the nuts, bolts, and the rings, right? And then we had scrap. And scrap was all kinds of junk. So you can imagine, if you want to train a model of scrap, that's going to be very difficult because it's everything. So instead of training a model for scrap, maybe we can introduce a rejection class. You can also think of it as saying, even though we only have, for example, nuts, bolts, and rings, maybe it's better to say it's neither of those than to say something that's slightly wrong. And it depends on the application whether that's a sensible choice or not. So you can also think of it as like, if an object is close to the decision boundary, the probability of making errors is actually high, right? Because a small change in the measurement could have put it on the other side of the decision boundary. So for example, this example here, if you put a measurement right there, maybe it's slightly closer to this one than this one up here, but you would not feel completely comfortable saying with any kind of certainty that it's one class or the other, right? So maybe it's still better to say, yeah, I'm not going to make a decision here. So the rejection class is a way of dealing with that, and we call that omega 0 here. And we put it in this augmented set of classes here, omega plus here, where we start with omega 0 and then to 1 okay here. What we must do to make this work is specify a cost. And we talked about the cost last time. But what's special here is we must specify the cost of rejection for class K. So what's the cost if it's truly class omega K? What's the cost of choosing omega 0? And if we take this and plug it into the whole Bayesian framework there, what we must compute here is the sum for each of the classes in the augmented class set here of the cost times the probability of the class given the observation. And actually, we only need to compute this from 1 to k. So the computation is essentially the same as before. Only there's a cost associated with it here also. So if we're doing minimum risk with rejection, so where we have the case of uniform cost, all errors cost the same. So we choose the cost of rejection to be the same for all classes. So we call this C REJ here. While the cost otherwise is the minimal conditional risk here. Then we choose as the class omega 0 here. If the cost of this rejection here is less than this minimum, we can otherwise get with the classes we have defined. Otherwise, we choose the most likely class. So that's like putting a threshold on the value here. It's like saying this maximum term down here has to be above a certain threshold, otherwise we're not going to choose anything. Again, imagine that all these, for the different classes here, are almost the same. Maybe it's better to not make any decision at all. So the maximum posterior probability, so the probability here is always both greater than 1 OK, because you have k classes. And if they're all equally likely, then it's 1 OK. And because they all add up to 1, it means that if one is smaller, then another one is bigger, right? So therefore, the minimal conditional error probability is bounded by 1 minus 1 OK here. And that means that if this cost of rejection here is larger than 1 minus 1 OK here, it is never chosen. You can also define a rejection rate like this here, which is the integral over P of set, the PDF for set here, for a set where this is the case that the cost of rejection is below. Good. So let's take a 10-minute break before going on with the section. Let's say we start again at, what should make it? Let's make it 25 past 11. All right. All right, let's get started again. And the last topic we'll be talking about is detection. So what is detection? Detection, you can define it as a problem of deciding between two classes. And it's essentially the same as hypothesis testing. So you know this very well already from your the statistics you did on Met 4, for those of you who did that, right? That's a detection. There's many other problems that are also detection. It's used, well, we can think of things like mine detection, burglar alarms. Digital communication is also based on detection, right? Because what is a digital signal? It's 0 and 1s, right? So you got to detect whether there's a 0 or 1. And the justice system is also based on detection, right? Or hypothesis testing. It's guilty or not guilty. It's a binary decision. And a lot of the things you can consider in connection with hypothesis testing, you can also consider in the case of the justice system, such as would you rather have an innocent man convicted guilty, then guilty person convicted innocent or not guilty. Right? Yeah. It is an extremely important special case, as you can guess from this. And actually, nowadays, I think there's a lot of machine learning applications where what you have is actually, you have, like the block diagram we had earlier, where you had all the branches, one for each class, right? A lot of modern machine learning actually works by having all these models running in parallel and then having essentially a detector on the output. You can also say this is very similar to having an objection class. Yes, it is. An example of this is image tagging, right? So because in an image you can, it's not a matter of whether you have a horse or a cow, right? You can have a horse and a cow. So you can have multiple labels assigned to one object. And then a common way of doing it is simply having all these models for different classes running in parallel and then simply seeing it as a detection or rejection problem for each and every one. Yeah. And if it, the nice thing is that you can trade off different types of errors for us here. And you can do it in a simpler way here than you can when you have many classes. Actually, the way you do this, if you prefer one type of error over another, the way you do this in the Bayesian classification that we looked at before is via the cost. If there's a type of errors you don't want to commit, then you just make the cost of those errors very high compared to the other ones, right? But in the two-class problem, it's much simpler and we can analyze things in more detail. So if you use a map classifier to choose between two different classes, omega 1 and omega 2, then the probability of omega 1 given the observation is given by this expression, it comes from Bayes' rule. And similarly for the class omega 2 here, then if this probability is larger than this probability, we choose omega 1, right? Otherwise we choose omega 2. We can also write it like this here. If you rearrange these terms here, so you take and divide by P of z given omega 2 here on both sides, you get this expression here, and then you divide by the prior of omega 1 on both sides, you get this expression. So you can see actually what you're comparing here is the ratio between the two likelihoods. And oh, by the way, I should explain this maybe again.
This is a permit?
No, it's not. So if you're looking to determine the probability of a class given the observation, then with Bayes' rule, you could express this as P of z given omega k times the prior of omega k and then divided by P of z. So this one here, when we're looking at like this P of omega k given z, then we're saying that the unknown here, the variable, is the class. At this point, this is just some vector we observed. So at this point, this is a constant vector. Then when you convert it into this type of distribution here, the way we looked at it was say, this is the PDF of the data for the different classes, right? So we're saying, oh, given the class, what's the distribution of the data? But we just said that set is actually a constant here. So what we're really looking at here as the variable is this thing here. So you keep this fixed and you look at the different classes over here. This is not a probability. It's not a probability density function. It's not a probability mass function. This is why you call it a likelihood. Because the quantity you're changing is the one that it's conditioned on. It's a probability in set, it's not a probability in omega k here. So that's why we call it a likelihood. And we don't refer to it as a probability or probability density. If you're saying, given a particular class here, and then looking at set, then set is the variable. Then it is a probability density function. Get the distinction? we get this thing called likelihood ratio. It's simply the ratio of the likelihood for the two classes here. And then we can compare this L here to the ratio between the two priors. We can also take the logarithm of this L here, like this here, and compute this lambda here of set. And then we have this T, the threshold, which is a logarithm to the ratio between the priors. You can also say this is a test statistic and this is the threshold. And we're looking, is the test statistic larger than or smaller than the threshold? Yeah. The thing is also that if you look at the one-dimensional case here, and we have a threshold T here, and down here it's one class, and up here it's a different class. If we move the threshold for deciding omega 1 further down this way here, there'll be less of omega 2s that are classified as omega 1, but there'll be more omega 1s that will be classified as omega 2s. Right? And the other way around, if we move it up. So the point here is that this thing, this threshold T here, it actually gives us control over the kind of errors we commit. You have the same thing in the justice system, right? Was it Thomas Jefferson, or who was it who said that better than 1,000 guilty men be found not guilty than one innocent man be convicted? That's the principle of detection in the justice system, right? It's a much bigger problem to take an innocent man and find him guilty than it is to let guilty people go free. Right? So we adjust the threshold, right? And this is why you have phrases like, we all know it from the TV shows, like beyond reasonable doubt and all those kind of phrases there, right? They adjust the threshold. Okay. If you have normal distributions, you can express this likelihood ratio here as something like this here, where these are Mahalanobis distances, you could say, and these are just some quantities involved in the determinant of the true covariant information here. If the covariant informations are the same for both classes, so the distributions for the two classes are the same, then this becomes much simpler. So this is much like the linear discriminant classifier we had before. You get a simpler expression like this here. And this is a Mahalanobis distance right here. So the type of errors here, so if the class is truly omega 1, and we choose omega 1, we make correct decision 1. If it's truly omega 2 and we choose omega 2, we have correct decision 2. If it is truly omega 2, but we choose 1, we can call type 2 errors. If it's truly 1 and we choose 2, it's type 1 error. I can never remember how this is with type 1 and type 2. It is much easier to think of this as the alarm problem, where class 2 here is that you sound the alarm, then sounding class 2, sounding the alarm, even though there's no reason to do so, then that's a false alarm, right? If you should have sounded the alarm, but you didn't, it's a missed event, right? It's a miss. Then you can also call it detection or hit, or true positive, or true negative. So if you look at the probability density function of this test statistic for omega 2 for normal distribution, with equal distributions between the two classes here, you can see they have the same shape, just have the same distribution but different means. Then, so this is the distribution for one class, this is the distribution for another class of this test statistic. Here we have the threshold. You can see that here, if this is the true positive we have here, and this is the true negative we have here, then if you put the threshold here, then the area under the curve here, that's a miss, right? The alarm was supposed to go off, but it didn't. That's a miss. On the other hand, If nothing is going on and we sound the alarm, then that's a false alarm. That's the area under this curve here. And you can see here that by moving T around here, you can change the size of these areas, right? But you cannot make both of them small at the same time. So you can't say, I want both guilty people to be found guilty and innocent people to be found innocent. No, you cannot do that. If you choose a certain threshold, it's going to mean a certain probability of having false alarms and a certain probability of misses. That's the way it is. Now, the distribution might be far apart, such that you virtually have no errors, right? But that depends on whether it's a simple problem or a hard problem. And most problems we work on are hard, right? I remember many years ago they were talking about, because the referees in football, they always make mistakes, right? There are these famous examples where there was actually a goal, but the referee missed it somehow. So they were talking about, now they have this technology, but back then they were talking about it. They want to put the sensor in the football and then detect when it's in the net, right? And then they said, oh yeah, it has to be correct 100% of the time. I don't think, if the future of my company depended on it, I don't think I would take the contract. And that's also nonsense, right? It doesn't have to be 100% correct. It just has to be better than the stupid referees, right? They make mistakes.
Yes.
Yeah?
Question, can we, instead of taking apart the means of the distributions, can we fix or like pretend that they are narrow?
Yeah, but that's like, okay, so you can make the mean, if you have an easier problem, the means may be further apart, or the distribution might be narrower, right? So if the distribution is narrower, then of course you'll have fewer errors. But what does that mean? If you're working on a problem, what does it mean you cannot change the distribution of data, right? What you can do, however, is that you can try different features. So if you're recognizing visual objects and you have some features and you're trying to detect something and it looks like this, maybe you should try different features, right? Because you cannot massage the problem into mysteriously becoming easier to solve the way it is. No way, right? And if you're changing the features, you're essentially solving a different problem. Yeah.
Another question. Does it have any meaning in this case to introduce a rejection class? Does
No,
it actually,
no. I
it
would
has
say
to be yes, it has to be 1 or 0.
yeah, okay. You can have a dead zone in the middle if you want. It would correspond to having a dead zone in between them, where you say you don't know. But I think the normal thing here would usage of a rejection class in this connection would be that you have a model for one of the classes, but not the other. Let's say you have a model for a certain kind of object, but then you want to decide, is that object there or not? Right? Do you want to train a model for not? No, that's going to be super complicated. That's everything else that can happen in the world, right? Then the rejection class would be a very nice option. But you're right. You could actually do it here. You would just introduce like a dead zone in the middle where you wouldn't make a decision. Yeah.
Isn't that still a miss type of?
Yeah. Yes. But maybe it makes sense for the problem. I don't know. This is like an arsenal of weapons we have at our, tools we have at our disposal, right? And then when we try to solve problems, we have to figure out what are the proper tools for the job. You can't really say unless you understand the problem. Same thing with the cost. Nicholas was asking you during the break, what about the cost? How to select the cost? I don't know. There's no rule for it. You have to understand the problem you're working on, like the nuts and bolts example. You know you're making money off some of these things if they're sorted correctly. And maybe your customers get really angry if they get a bolt in the rings. I don't know. And that means that should have a high cost. But then you really got to understand, you've got to understand the application, and probably you even need the marketing people and salespeople and stuff like that to quantify something like that.
So I guess like seriousness of the problem, like for example, Tesla's cars,
Yeah.
seeing if there's a person or whether to
Yeah.
choose.
Yeah.
That's a thing that should have a very defined cost
Absolutely.
compared to separating ripe tomatoes with not so ripe
Yeah.
tomatoes, let's say.
Yeah. Or finding hot dogs in the pictures on the internet. Do you guys watch Silicon Valley? And you can quantify the probability of false alarms and misses via integrals over these quantities here. It looks super complicated when you look at it like this. You think, oh, I got to integrate from t to minus infinity. How do I do that? But when you see it graphically, it's actually fairly simple, right? But the cool thing is that once you have quantified these probability density functions, you can actually compute what is the false alarm going to be, what is the probability of miss is going to be. So when you have the models of the different classes there, you can do these things. So here's what they might look like, these kind of functions for a problem. So, for example, one thing you often look at is the probability of detection versus the probability of false alarm. Because there's a trade-off there. If you want to detect everything, then you might also have a lot of false alarms. In fact, you're going to get a lot of false alarms, right? If every time there's the slightest chance of somebody's breaking into your house, the alarm goes and phones the police, right? Then there's going to be some false alarms among it, right? This is what you see here, that you can see here that if you want a really high probability of detection, let's say you want it here, then you're going to have an 30% false alarm rate. You think, oh, false alarms, that's not good. That's going to cost me money. So you say, okay, fine, I'll have 10% false alarms and then only 95% detection rate. Right? But the solutions you can get on this curve here, you decide which ones you want to have for your problem. Oh, by the way, if you're designing a mine detection device, how do you want this to be? Do you want a lot of false alarms or a few false alarms? I think I'll prefer a lot of false alarms. Right? If this is mine detection, you say, I don't like false alarms, I want my false alarms to be very low, let's say here, then your mine detection will only be detected in mines 80% of the time. That's not going to be good. It'll be dangerous to get any kind of insurance there. It's really expensive. Over here you see the different functions also as functions of the threshold. So you can see that here in this case, the higher the threshold, the lower the miss right here. But the higher the threshold, the higher the false alarm rate also. The probability of detection also goes up as a function of t here, right? If you go back to the example, here, the higher t is, right, the more of this we will capture, right? If t is up here, there's virtually 0 errors, but there's going to be a lot of false alarms. But the important thing to understand is that you can't get everything, right? There's no free lunch here. If you want a high detection rate, you're going to get false alarms. And you cannot, for a given problem, have both low probability of miss and false alarms. You see the functions here, one goes down, the other goes up here. But there is a point here actually where you can see that both of these things will go. About the same. But anyways, by plotting these kind of curves here, you can see what the trade-off is. and understand your problem.
Is curve B, because it looks like receiver operator characteristic, the ROC curve.
Yes. This is, okay, the receiver operating characteristic, that's a terminology that comes from digital communication, where you have to detect 0 or 1s. So that would be this kind of curve here. That's what you call an ROC curve. Yeah. And in the new versions of PR tools, you can actually get you can get these, aside from the usual way of assessing classifier performance. You can also get these ROC curves for the individual classes. Yes. You can see here also that the error rate here, you can express that in a number of different ways here. Most important in this one down here, we have the probability of false alarms times the prior for class 1, probability misses times the prior from the 2. So we talked about the mine detection example already. What about diagnosis of illnesses? That's a difficult one, right? If you tell people they have a disease but they don't, that's going to be terrible. On the other hand, if they have the disease and you don't detect it, then that's also a big problem, right? And also financially, it might be a problem. What's the cost of somebody dying from a disease versus the cost of needlessly putting people through very expensive scanning equipment and stuff like that? And these are the kind of decisions that doctors have to make it all the time, right? So when you go to the doctor and you say, my chest hurts, and he says, nah, it's probably nothing. He's just trying to save society's money. You look fine.
Matt,
Yeah.
I guess just to see if I'm thinking about this correctly, but like when I actually defend this in the exam.
Yeah.
Let's say, for example, diagnosis of illness.
Yeah.
I set the cost function so that maybe I get it right. Let's say 90% of the time. Compared to 99% of the time.
Yeah.
Right? But then I say, with the justification that it's sufficiently accurate to raise a red flag for the doctor, and so the doctor can be like, okay, it's 80% accurate, but that's still a good amount for me to be like, okay, let me double check with further lab.
Yeah.
Lab.
But you can argue like that, but you can also plot these things like this instead.
Yeah.
Because then we can see what it's like, and we can see if it's a simple or a hard problem. Your solutions are on these lines, right?
Yeah.
These are the different ones you can choose here. Like,
No, because
Yeah.
I mean, my point is more that, of course, I want it to be as accurate as possible.
yeah,
But thinking that if I try to make it as accurate as possible, there's a tiny chance that it could be wrong,
Mhm.
right? The trade-off could be that I could maybe make it not so accurate, but still raise a red flag for the doctor.
Yeah.
They're both arguably
Yeah,
good.
but this is why you should look at this instead. Because this is the space of the solution we can get, right? And then you can say, let's say, if we detach ourselves from the problem slightly and we think ourselves as scientists, right? Then we're investigating how well can we solve this problem. And we can plot this and we can go say, well, with the information we have at our disposal, this is what you can get. But you gotta tell me which one do you want, right? And because then people will say, well, I want high detection rate and a low false alarm rate. Well, you can't have both. You tell me where you want to be on the curve, right?
So it's the justification of that where I show you where I want to be on the curve that I have to make, because I can show you the exact space of cost, but I can have kind of subjective arguments
Yeah.
for either case.
Right.
That's what you wanna hear in the exam?
Well,
Apart from
if,
showing
but
you
if you
the
make
example.
this, if you make this choice, then you should be conscious of it, right? And you should be able to argue for it. Alternatively, I would say plot something like this and say, these are different kinds of solutions we can get here. Did you have?
Mostly, you said something about that the lines would tell us which one we go for, basically. But isn't the context really important in that situation? Because
Absolutely, but this is why I don't want to make the decision, right? This is why I want to show the plot.
So you would want us to maybe show multiples and then decide
This, you want me to this, you want me to that. I want you to be independent, clever young people who think about what you're doing and you do what you think is the appropriate scientific thing to do.
Well, I'm not just going to show you a plot and say, well, that's just how it is. You want us to argue for this.
Yeah,
We're gonna argue.
but think of it this way. This, I mean, if you come up with one particular choice there, you're saying, I think this is the way to do it. Okay, fine, argue for that. If you show me this, on the other hand, you say this is what is attainable. Here you're trying to analyze the problem and see what can be done. Right? You say, oh boy, this looks like a difficult problem. As opposed to just arbitrarily picking something. Right? What about speed control? The police, they do this all the time, right? With, well, they've gotten very aggressive lately with these. Is it radar or what, laser or what is it? I don't know. What's the cost of the different kind of errors there?
This again can be very subjective, because if I start to present this to the police, they're like, yeah, put all the errors that you can, rake in all the fines.
I promise you, they don't want that, because that's going to lead to a lot of angry citizens and judges overturning their decisions, and that means a lot of paperwork for them and so forth. So this is also why, if you ever get a speeding ticket, you'll notice that they will actually subtract the value there from the measurement they actually made. So if the speed limit is 50 kilometers an hour and you were going 55, they will say that it's 52 or 53 or something like that. Because they absolutely want to be certain that when they give you a fine, you were over the speed limit. And death sentence based on evidence or whatever. You want to be damn sure that you're not making a false alarm, right? But again, you've got to dive deep into the application and the domain to be able to quantify these things, right? So here's an example from the book here, bottle recycling. So you've probably seen these at the supermarket, right? So there's some kind of camera or something, we can do some measurement here. This one takes a picture of the top of the bottle here, and it wants to detect if you should throw it away or accept it. And of course now you can quantify it, right? Because if you're throwing away a perfectly good bottle there, you're losing money, right? And then maybe it's a bit hard to quantify what it costs you when you send a bad bottle back to the bottling plant. You probably have angry customers. That's not good. Never good. So here are the images acquired for two different bottles. Here's a new bottle, and here's an old one where you have some decay or defects. And here's an example of the estimated probability density function for the two classes you can see here. You can see here that there's some area here where there's some overlap between the PDFs. And here you have the ROC curve. It seems to be doing pretty well, actually. And here you can see here how easy it is to actually compute one of these. Computer, there's a function RC. Actually, I think it's changed. There's a note about it in Moodle. how to compute these ORC curves. Okay. So, and I think I said this already, but it's important to understand the overlap between the traditional PDFs to determine if it's an easy or hard problem. This depends on the difference between the mean and or the covariances. As we've seen, we can trade one type of error for another, but there's a fundamental limit to how accurately we can solve a given problem. If the error rate is too high, we need to find better figures to solve the problem better, or different statistical model in the future. Right? That's the only way. That's the only way we can massage the problem into something that's easier to solve. Great. That was it. Any questions? No. I will see you on Wednesday.
Yes.